Hello everyone, welcome to another video in the Mathematics Essential series. I did say in a previous video that I was finished with trigonometric identities in this series. However, I was forgetting that I did say I would make videos that talked about the geometric intuition behind all of the trigonometric identities that I did not prove geometrically. So I will cover all of those in this video. Okay, now we did prove 3 of these geometrically. Okay, we proved trigonometric identity 3, the Pythagorean identity, and the sum formulae, which are identities 10 and 11. Okay, so if you've watched those videos, you will understand the geometric reasoning behind these identities. Okay, so let's go ahead and cover the rest. And I'll say at the outset that understanding the geometric pictures behind 3, 10, and 11 will serve you well for understanding the rest. Okay, so let's talk about identities 1 and 2. Okay, they're known as the reflection identities for geometric reasons as follows. Okay, now for many of these diagrams, it's probably more helpful if you take a look at them yourself and really convince yourself that they do correspond to what the identities say. So here, we see that we have 2 angles of equal magnitude in the unit circle. We have theta and negative theta. And negative theta is just the angle theta measured clockwise from the positive x-axis. And you can see from the diagram here that the points P and Q, okay, they have the same x component in their coordinates. Okay, they both have A as an x component. All right, there's A, and that's indicated by the blue line. Okay, right, but you can see that they have y components that are of the same magnitude but opposite signs. So you can see that this distance, right, this y distance and this y distance are of the same magnitude, but of course, since one is below 0 and one is above 0, they must have opposite sign. Okay, so they have these components b and negative b respectively. Okay, so that's why the cosine of theta is equal to the cosine of negative theta. Well, that's the geometric reason. And that's also why the sine of negative theta is equal to the negative sine of theta. Okay, and you can see this from writing out the points P and Q as components in terms of sine and cosine. Okay, so those are the reflection identities, trigonometric identities 1 and 2. Okay, all right. Now let's get on to identities 4 and 5. Now, identities 4 and 5 are really just the Pythagorean identity in disguise. And the Pythagorean identity is just a special case of Pythagoras' theorem. So really, all 3 of these identities are just Pythagoras' theorem wearing different kinds of balaclavas, so to speak. Now, here is the geometric idea behind the Pythagorean identity. Okay, we have a right-angled triangle that has a hypotenuse of length 1 because it's the radius of the unit circle. Okay, we have this angle theta here, all right, and we know that the side lengths we know what the side lengths of this triangle are in terms of theta. So the adjacent side is the cosine of theta, and the opposite side to the angle theta is the sine of theta. Now, remember when we proved trigonometric identity 4, all we did was divide through by the cosine of theta squared. We did this on both sides, okay, and that's a quick way to prove trigonometric identity 4, okay, because this right-hand side here is the secant of theta. That's what trigonometric identity 4 says. It says that 1 plus the tangent of theta is equal to the secant of theta. Now, dividing through by the cosine of theta squared is the same as multiplying by 1 over the cosine of theta squared. Okay, so what's happened here is we've really just taken the triangle in this picture and scaled it by a factor of 1 over the cosine of theta. Not 1 over the cosine of theta squared, 1 over the cosine of theta. Okay, so let's imagine we picked that triangle up and we moved it down here. All that's happening is the side lengths are being scaled by a factor of 1 over the cosine of theta. Okay, so what happens is that the hypotenuse is no longer of length 1. Okay, it's of length 1 over the cosine of theta, which is the secant of theta. Okay, now the adjacent side ends up having a side length of 1, and the opposite side ends up having a side length of tangent of theta. Okay, so it's just the same triangle in the Pythagorean identity, but it's been scaled. Okay, and scaling a triangle changes none of the trigonometric relations between angles and side lengths, etc. Okay, now for trigonometric identity 5, okay, this one here, okay, one way that we proved that was to do just like we've done here, but divide through by the cosine of theta squared instead. Okay, sorry, the sine of theta squared instead of dividing through by the cosine of theta squared. Okay, so similarly, all that would happen is that we would be scaling this triangle by a factor of 1 over the sine of theta instead of 1 over the cosine of theta. Okay, and what happens now is that the opposite side to the angle theta ends up having a side length of 1. Okay, this side here ends up having a side length of cotangent, right? That's the adjacent side to the angle theta, and the hypotenuse of the triangle ends up having a side length of cosecant of theta, because that's 1 over the sine of theta. Okay, so nothing really different is going on than what we have with the Pythagorean identity. Okay, so I should just comment that if you applied Pythagoras' theorem to this triangle, you would get trigonometric identity 5. And if you were dividing by the cosine of theta instead of the sine of theta, you could apply the Pythagorean theorem, and you would derive trigonometric identity 4. Okay, so that covers identities 4 and 5, which are just the Pythagorean identity in disguise. All right. Okay, now let's cover identities 6 and 7, which are known as the coangle identities. Okay, and the reason they are called that will be clear from a diagram. Let's find the diagram for the coangle identities. Here we are. Okay, so here we have a right angle triangle. Okay, we have an angle theta, side lengths A and B, and we call the hypotenuse C. All right, we know that this angle here is always going to be pi over 2 minus the other non-right angle theta. And that follows from the fact that the interior angles of any triangle must sum to 180 degrees. You know that one of the angles is pi over 2. You've already introduced notation for one of the other non-right angles, so you can express the other non-right angle like we've done here. Okay, now if we call this one the angle, okay, well, this one's the coangle and vice versa. All right, so if we take the sine of pi over 2 minus theta, all right, we get, okay, the opposite side over the hypotenuse, okay, A over C. But that's exactly what we would get if we took the cosine of theta, okay? In this case, it would be the adjacent side over the hypotenuse, okay? And a similar thing happens if you took the cosine of this angle here, all right? You end up getting, I don't know what happened here. Oh yeah, well, that's the identity, okay? But if you took the cosine of pi over 2 minus theta, well, that's the adjacent side, that's B over the hypotenuse, and the sine of theta is B over the hypotenuse, the opposite side of the hypotenuse. So you can see that they are equal as well, okay? So that explains the coangle identities. So we can go ahead and cross them off. Okay, now these identities here, you can think of as period shift identities, okay? And this term period comes from the fact that cosine and sine are periodic functions, and their period is 2 pi. All that means, okay, all that's calling a function periodic means is that the graph keeps repeating itself, all right? But it keeps repeating itself over some interval, and that interval is the period. So in plain English, saying that cosine and sine are periodic functions with period 2 pi just means that the graphs of those functions repeat themselves every 2 pi, okay? And you can see that here from the graphs of sine and cosine of x. Now, if you consider the arguments of sine and cosine, okay, well, if we took the cosine of theta, for instance, so let's just focus on trigonometric identity 8. If we took the cosine of theta, right, well, you know what the graph looks like. But if you took the cosine of pi over 2 plus theta, that corresponds to shifting every point on the graph, pi over 2, to the right, okay? And you can see, and similarly for the sine of pi over 2 plus theta, and you can see with these graphs what happens when you take one of the graphs and shift it pi over 2 to the right or to the left. You see that the graphs will line up, and I've tried to emphasize that with the green tick marks. Take any of these graphs, shift them pi over 2 to the left or to the right, and you will see that the green tick marks will, you will basically get the other graph. That's what I'm saying, okay? So that's not just a geometric picture for these identities 8 and 9, but also for the coangle identities, which you can also think of as quarter period shift identities, right? Why quarter period shift? Well, you're shifting the period by pi over 2, and pi over 2 is 1/4 of 2 pi, which is the period of these functions. Okay, now let's consider the, let's do the double angle identities, okay, which are identities 14, 15, 16, and 17. We'll just focus on the first two. Okay, now remember how we algebraically proved these. What we did was take the sum formulae, okay, and then just set phi equal to theta in both of the sum formulae, okay, and that allowed us to derive these expressions on the right-hand side. Okay, so that's a good indicator that a geometric understanding for the these double angle formulae, 14 and 15, would come from the geometric interpretation of the sum formulae, okay? So it doesn't have to. There are a lot of different ways you can geometrically visualize these identities, okay? These are just some ways, okay? So you could take this geometric diagram here, okay? This came from our geometric proof of the sum formulae, right? But instead of having two different angles, theta and phi, okay, this angle here would just be equal to theta. So yes, that would change the triangle, and that this triangle would no longer fit inside this rectangle, but you could just choose another rectangle such that this triangle, when this angle is theta, would be inscribed perfectly within that rectangle, and you would have a very similar image to the one you have here, only every instance of phi would be replaced with theta, and that would offer some simplification. So for instance, here we have the cosine of theta times the cosine of phi. Well, if phi was equal to theta, this would just be the cosine of theta squared, right? Okay, so that's how you would end up getting a geometric idea for those double angle formulae. Now, when we proved the other two double angle formulae, all we did was we made substitutions into this one for the cosine of theta squared and the sine of theta squared. And we made those substitutions by rearranging the Pythagorean identity for the cosine of theta squared or the sine of theta squared, depending on what substitution we wanted to make. So there's no additional geometry going on there. Okay, you could just take the geometric picture you would get for these identities here, which is just this geometric picture with this angle replaced with theta, okay, and everywhere else as well, replacing phi with theta, okay, and you would have expressions on the side length. So for instance, like I said, this expression here would be the cosine of theta squared, but you know that that's also equal to 1 minus the sine of theta squared, okay? So the only additional geometry going on here over and above this diagram would be the application of the Pythagorean identity, and you understand the geometry behind the Pythagorean identity. Okay, so really there's nothing extra going on with these, okay? So let's cross off 14, 15, 16, and 17, okay? And let's move on to the half angle formulae. Okay, and basically I'm leaving you with a diagram for the difference formulae well, I will explain the difference formulae, but then I will give you another diagram that explains it in a different way, and you can sort of think about that one as a bit of a challenge, I guess. Okay, let's talk about the half angle formulae now, these ones. Okay, now the half angle formulae, okay, remember we just got these from rearranging both of these identities. So there's no extra geometry going on there. Okay, it would really just be this picture as well, where this angle is theta. Okay, but there are sort of geometric diagrams that do sort of explain these on their own in terms of half angles. So if you want to see those, I encourage you to look them up. I'm sure you can find them somewhere on the internet. Okay, now let's talk about the difference formulae. Okay, now with the sum formulae. Okay, remember when we proved that, what we did was we considered a triangle, all right, and this angle here was theta, not theta, it was phi. Okay, so when we were proving the sum formulae, we took a triangle like this, ignore theta for the moment, and then we imagined rotating it, keeping the vertice at the origin fixed, so we rotated it around the origin by an angle of theta. Okay, then we imagined inscribing that triangle inside the unit circle, so this here, this line segment was part of the x-axis, this was part of the base of the triangle here, okay, and that's how we got this angle theta here. All right. Now, one way to think of the difference formulae is instead of having the triangle, rotating it by an angle of theta, all right, you just imagine instead this image here. So we have this triangle with an angle theta, all right, and we just have this triangle here with an angle of negative phi. Okay, so that's just the angle phi, but measured clockwise from the positive x-axis. Now, what you can do is just pick this triangle up, flip it over the x-axis, so you kind of reflect it through the x-axis, and then stack it on top of this triangle here. So you'd have something like that, and then you'd have negative phi, right? And if you did this, what you would have is an image or a diagram just like the one we've got here, really, okay, but this angle would be negative phi. So then you'd have to go around and replace every instance of negative phi, okay, in the expressions in which phi occurs, okay, and then everything would work just like it did in the sum formulae, okay. So there's no real extra geometry to understand, really. All that's happening is that one of the angles has been measured clockwise from the positive x-axis, okay. So that takes care of the sum formulae, okay, and I think I misspoke before. I said I would leave you with another diagram for the difference formulae. I meant to say I will leave you with another diagram for the half angle formulae, okay. So let's take a look at that, and I actually won't explain this one because I think it would be nice for you to reason about it yourself and come to an understanding of the half angle formulae. All right, so what this diagram would actually get you is an expression for the tangent of a half angle. Okay, so consider that, all right, and just keep in mind that the tangent of any angle is the sine of that angle over the cosine of that angle, and see if you can come to an intuitive understanding of the half angle formulae. And even though we have expressed the half angle formulae in our list like this, remember, you can always write it like this instead. So 18, okay, you can write like this, right, which equals 1 minus the cosine of just theta rather than 2 theta over 2. And you can do a similar thing for this identity too. You can write the cosine, this is squared. Okay, you can write the cosine of theta over 2 squared equals 1 plus the cosine of theta over 2. Okay, so if you'd like, you can play around with this diagram that I've provided here and see what you can deduce from it about the half angle formulae. Okay, so I hope you enjoyed this video. I hope you found it helpful. Feel free to give it a like and share it around if you did. If you have any questions about what I've done, just leave a comment. And if you would like a notification when I upload a new video, just subscribe to my channel. Until next time, bye for now.